So I'm Melanie. As Dougal said, I'm from Bonn. I'm a master's student there, and I work with Richard Stancliffe on theoretical models of neutron capture elements. So I'm very happy that I got the chance to come out here to actually work on the observational side of that problem. I didn't have any insight into that before, but you'll see what I did. So chemical abundances of metal core stars. I worked on it with David Young. And why do we even care about metal core stars? Well, they contain a lot of information about the very early universe. So we have to study them if we want to find out where and how and when the first low-mass stars formed, for example, how galaxies formed. But I'm particularly interested in them because they can tell us a lot about how elements synthesized in our universe. So after the Big Bang, there was just helium and lots of hydrogen, traces of lithium maybe, but everything other than that has been synthesized in stars. So everything heavier than helium is what we call metals. So metal core stars are those that have not, or they have formed when the interstellar medium has not been as enriched in those metals from previous generations of stars. So they still contain imprints of the early nuclear synthesis that was going on, and that's why they're so interesting. So normally, when a star produces heavier elements, it takes light ones, fuses the nuclei together, forms a heavier one, and that process releases energy. So an example would be we take four protons, fuse them together to helium. That's what the sun is doing at the moment. The problem is just that we can reach iron with that, but we can't go any further because iron is the most stable element, and if we want to fuse those nuclei together, we actually need more energy than the process releases, so stars can't do that. Also, when we look at the production of heavy elements, which means the mass number greater than 56, we already have huge nuclei. So iron, for example, has 26 protons. And these protons have a huge Coulomb barrier, so all the other nuclei can't really come close because they feel this huge repulsion. So we can't really have charged particle reactions happening. So what we need is neutron particles that do not feel this Coulomb repulsion. And that's why neutron captures come into play, because they're really the only thing that effectively can produce heavy elements. So what happens when a seed nucleus captures a neutron? We can see that best in this slide here, which shows a nuclide chart, which means we look at different proton numbers and different neutron numbers and all the different isotopes in this range. And the black ones are the stable ones. So if we start off with a seed nucleus here, and it captures a neutron, it then forms the next heavier isotope of that same element. And it just keeps doing that until it reaches somewhere where it's unstable. An unstable element then decays back and keeps capturing neutrons. But that is only true if it has actually enough time to decay. So for this decay to happen, there is a certain lifetime. And it might happen that there are enough neutrons around that it can actually capture another neutron before it decays and can go all the way up to here. That is the case when there are really high neutron densities in our scenario. So you can see these two different processes. We call them S process, that's this one, that's the slow neutron capture process, because neutrons are added quite slowly. While here we have the R process, the rapid neutron capture process. And they flow through different sets of nuclei, and therefore they can produce totally different abundances, or abundance patterns for that matter. So while the S process stays very close to the value of stability, where these stable elements are, the R process can reach very far into the regime of the unstable nuclei. But for that, as I mentioned, different conditions are needed. So the neutron densities that are needed for the S process are about 10 to the 7 neutrons per cubic centimeter. And for the R process to have enough neutrons to add them so rapidly, we need many, many more neutrons. And we're talking about many orders of magnitude here. It's about 10 to the 25 neutrons per cubic centimeter. Obviously, these two processes can therefore not happen at one at the same place. They have different sites where they happen. So for the S process, one of the main types are AGB stars, which are asymptotic giant branch stars. And that's sort of a phase at the end of the life of low-mass stars, intermediate-mass stars. But these evolve quite slowly, so it needs actually some time for the S process to be enriched in the interstellar medium. On the other hand, the R process needs much, much more extreme conditions, and we are not really sure where that can happen. The sites have not really been confirmed yet, but for example, supernova are associated with the R process. But also things like neutron star mergers have been considered. And these processes happen very fast, and so they can already happen very short time after the first nuclear synthesis happening. So in order to really understand how heavy elements form, we need to have models to explain observations, and the other way around, we need observations to constrain the models. And that's sort of what I've been looking into at this point. I started with the Globular Cluster M80. That's a very rich cluster, it's very dense, but it's not been studied very well. So there is a study about 10 years old from Cavallo et al., and they found that europium, which is an arc process element, that has been quite enriched in this cluster. So we decided to get better data, better resolution, look into that cluster again, and find out what's happening there. So the first thing which you need is obviously the observations. So I was provided with observations from the Maggelan Telescope, that's in Chile, and it has the MAG spectrograph. And you see it has quite a good resolution here. That's about 3 to 5 times higher than the data that the other study used before. And I studied 2 stars which are near the tip of the red giant branch. So the first thing with those spectra, we want to find out the stellar parameters, which means we want to know what's the effective temperature, what's the surface gravity, what's the velocity of our star. And to do that, you have to measure all the absorption lines in the spectrum. And I measured the equivalent width of those lines with 2 different approaches. So first I started just manually, which you can see here in the screenshot from IRAF. Just line by line, measure them, see what happens. And then I used DowSpec, which is an automated program basically. It can identify the absorption line, it can put continuum, it can measure the equivalent width, just all automated. And to get a feel for how uncertain these measurements are, I then compared these 2 different approaches, which you can see here. So on this axis you see my hand measurements, and here you basically see the difference in between those 2 measurements. And what I basically looked at is the dispersion around this linear fit in the middle. And I then used this dispersion to quantify what's a good fit, like what has been good measurements, what's not so much. So the red crosses you see there, they all deviate from that linear fit by more than 2 standard deviations. And that we considered outliers, and we didn't consider them any longer. So we were left with 175 measurements of iron lines in this case. So once you have these equivalent widths for the lines, you can go on and measure abundances from these lines. And for that I used MOOG, which is a program that does exactly that. And we use here a one-dimensional stellar model atmosphere and local thermal equilibrium. And with those inputs, MOOG then converts on a line-by-line basis the equivalent width into an abundance. And here we see a typical output from MOOG, where we have the abundance as a function of the excitation potential, the reduced equivalent width, or the lambda, so the wavelength. You would expect, or it shouldn't be the case, that these abundances vary within a star. They should not depend on what line it is. The abundance is the abundance of the star. So by changing the model atmosphere that we put in, MOOG can then redo all of that, and we can find that model atmosphere that removes trends that could be in here. So here you already see that the trend has been removed, and that leaves us then with the stellar parameters for the 2 stars. So once we have the stellar parameters, we can use these model atmospheres that describe the star best to actually measure abundances of other elements. So here you see a barium line, and I basically just did a spectrum synthesis to describe that line. And there are 4 parameters that you can vary to describe the line best, and I varied the abundance, which gives me the strength of the line, the macroturbulence, which gives the broadening of the line. Then there's the radial velocity, which can shift the line. And of course, the continuum also has to fit. And well, when you find the right set of parameters there, then as you can see there, you can describe the line pretty well. Again, I did a lot of them manually, just to see what these typical values are, how they vary, what freedom I have with, yeah, it's quite a subjective thing if you want to do it manually. So then after that, I used an automated version of that whole process, which basically used chi-square minimization to find the best set of parameters. So from these, analysis, I can then, or I did actually measure 12 elements, neutron capture elements, so heavier than iron, in these 2 stars. But I'm only going to show you 2 of them here, the 2 most important ones, or the 2 most interesting ones. So here you see my 2 stars and the result that Cavallo found for the whole cluster as an average. And the first line is the metallicity, And then the second and the third line are the two interesting abundances of lanthanum and europium. And they are so interesting because lanthanum is produced by the S process, and europium is produced by the R process. So if you compare them, or if you look at the ratio of them, you can find out a lot about how these processes happen relative to each other, which one was more effective, which one was less effective. So these abundances of lanthanum over europium have been studied a lot. And here's an example from Roger et al., and they measured in, I think, 160 field stars that lanthanum over europium ratio as a function of metallicity. And what they also did is they looked at models. They looked at AGB models and found out what minimum ratio they would expect if AGB actually pollutes the interstellar medium with S process elements. And that's that blue line here that gives you a minimum ratio which you would expect for S process pollution. So all the blue crosses above that show S process elements, and all the red stars down there do not show S process elements. So these then have been classified as R-only stars. So they only show enrichment of the R process. And the two green crosses here, they're actually the stars that I measured. And you can see they fit in very well with that portion here that has not been enriched by the R process. By the S process, sorry, only by the R process. And that's quite unusual. It's not unseen, but it gives us a really good opportunity to study that further. Because this cluster now has lots of stars that we can study. We can get much higher precisions from that, and we can then learn much more about the R process. So to summarize, we look at metal poor stars to find information about the early universe, and in particular in this case about the nuclear synthesis that happened in the early universe. And I measured abundances for 12 elements, for 12 neutron capture elements in 2 stars in M80. And especially the lanthanum over europium shows us that M80 has pretty much only been enriched in the R process, not so much the S process. So that gives us a really good base on which we can study the R process much further. Thank you.
Great, thank you, Melanie. Questions?
So did data only have 2 stars, or
Yeah.
so there's no more data?
I don't know what other data he has, but on that cluster he said he only had those 2 stars. And there are also stars that Cavallo now studied before.
How many were in Cavallo?
10.
Yeah. So how does your lanthanum to europium ratio compare with other globular clusters of similar metallicity?
I don't know. So I only really found these field stars to compare them on very well. Actually, I think Jennifer Simmer also looked at them before, at these field stars, but I haven't looked at other globular clusters.
Any other questions for Melanie?
Well, David had a guess on that. He said it's rather unusual for that metallicity, that it's rather on the higher end of the metal poor globular clusters, and that's not been seen so much in that detail. I don't know what it says. He didn't back it up with any references.
How well did your the metallicity of your stars match the metallicity of your globular? With it?
So with the globular cluster, you mean the Cavallo measurements, or?
Yeah. Okay. All right.
That's how well they match.
Right.
So the uncertainties on that metallicity are about 0.15 or so. So yeah.
You said yours are much higher resolution.
Yeah.
So
And also, I mean, these are now 2 individual stars, while the other one has been averaged over more stars.
No further questions? Okay, good. Thank you, Melanie.